So let's get on with it. Lecture 5 of our Introduction to Thermodynamics. Calling it an introduction, even though it's quite an advanced course. It's advanced from the sense, in the sense that it's an advanced undergraduate course, but there's another level we can go up, and there are a lot of interesting questions, thermodynamic, sort of fundamental questions about thermodynamics that I don't really want to talk about in this course, because this is like the first proper course in thermodynamics that you're having. Okay, so there are higher levels that you can go up, that maybe 4th year level and grad school level, but you don't need that first off. What you need now is a nice orderly introduction that gives you the overview of thermodynamics and gives you some feeling of how to use it. Some perspective, gives you a perspective. So there are plenty of questions that you can ask about almost everything that we're doing. And thermodynamics is a very interesting, very difficult subject. And another thing is, everything we're doing is equilibrium thermodynamics. And there are some very interesting recent results in non-equilibrium thermodynamics. Thermodynamics is alive and well as a research area. The so-called fluctuation theorems came out in the mid-90s, and I think they're pretty easy to understand because of the background that we've had so far in terms of phase space in classical mechanics. You've got if you know that, what we've done, especially UV theorem, the conservation of the volume under Hamiltonian flow, then it really makes a lot of sense, and it's fairly straightforward, but very interesting. We don't have time to do any non-equilibrium thermodynamics, obviously. It'd be nice to do it, but that's the next course in grad school somewhere. I don't think anyone here teaches it, but if you go to MIT or something, definitely, you'll see it. I'd really like to do an SP4 course, 4th one after next semester, but there are more, but the number of people taking it would be too small, and I've got enough workload as it is. So, Anyway, so today, how can last week's theory be applied practically? But the main points are these two. That so far we've only seen an entropy maximum principle. That's what we've actually used in calculations. But actually that's equivalent to an energy minimum principle. So today we actually prove that. We only prove it in one direction. And the other direction, if you want to try it yourself, you can, but you just get the gist. And the most important thing today, which is really important, really fundamental for the rest of your working life in anything to do with thermodynamics, is this one, thermodynamic potentials, and the Legendre transform representations. Okay? So today we're doing Callen chapter 5, and for this first bit about last week's theory, there's an excellent chapter in Zemansky and Dittman on the traditional approach to thermodynamics from around about the 1850s. And that chapter actually also goes into Kara-Theodori's approach from 1909, which is highly non-traditional. So just as an outline of today, let me just talk about the first point. Well, last week we proved the maximum work theorem, but actually if you think about it, if you had thought about it, well, you might have actually thought that there's kind of something a bit strange happening, because there are 3 facts which, if you look at them together, they seem to be contradictory. So, firstly, maximum work is delivered when the total entropy change in the isolated system is 0. So what that means is that the processes of heat and work transfer that occur inside the system are reversible, where this idea of reversibility is a highly idealized situation invented to understand the limit of efficiency. So, maximum work is delivered under reversible conditions. Okay? Conditions of reversibility. And the second point is, for reversible heat transfer, all heat transfer must occur between bodies of equal temperature or extremely close temperature. So this idealized quasi-static transfer of heat. Okay, so reversible heat transfer, we want maximum work to be delivered, so we want reversible heat transfer, and we want all heat transfers to occur between bodies of equal temperature. Okay. And the last point is, in fact, if you just contemplated the efficiency equation that we derived last week, you would have seen that in order to move forward, the entire process must involve a temperature gradient. And in fact, the larger the temperature gradient, the better. And the better the efficiency. Right? How can a large temperature gradient be achieved while all heat transfers occur between bodies of equal temperature? See, it sounds like it, doesn't it? So what's the way out of this? How do you solve this apparent contradiction? How do you resolve the apparent contradiction? Automotive engineers? Anybody? John? No job?
Oh, no idea.
Yeah.
CARNOT CYCLE.
Yeah. Why is the CARNOT cycle born? Why? You've all done at least 2 thermodynamics courses so far. None with me.
You need to for the you need so you basically need an isotherm and an isentropic process.
Or some process.
But then you need the one process to be between bodies of equal temperature.
Yep.
And one process to have a temperature gradient with delta S is equal to 0 for maximum efficiency.
Yeah, but how do you have a temperature gradient and delta S equal to 0? We saw last time, but quasi-static, you have a temperature gradient, but if this temperature gradient is big, you always have an entropy increase. You can't avoid it. What on earth is going on? Well, keep that in mind, okay? Keep that conundrum, that dilemma in mind. We'll see it solved in a few minutes, okay? Yeah?
You said that the temperatures are equal, so
between bodies that are transferring heat, yeah.
So, like, for example, in the previous lecture, do you mean just the system that goes from one state to the other, temperature is constant there, or for the
primary system and the heat reversible?
The heat reversible.
Okay, so keep that in mind. Secondly, today we proved that the entropy maximum principle at constant energy is equivalent to an energy minimum principle at constant entropy. Okay. And this is extremely important, and it's the foundation of the rest of this. Right? You need that. The reason why all this works is this here, that there. And the important point today is, what if internal energy volume, or number of moles of particles, or entropy volume, or number of moles of particles, are not the variables controlled in the laboratory? Okay. What if they're not? What if some other combination is under control, such as temperature, volume, number of moles, or temperature, pressure, number of moles? Obviously, if you do an experiment in the lab, this is the most common situation. Okay. This is also a very common situation. Or entropy, pressure, number of moles, or temperature, pressure, chemical potential. This is also a common situation, because the chemical potential is often controlled by some kind of electrical field. You don't know any examples yet, but you will by the end of the semester. Or, in fact, next semester, more next semester than this semester. So what is the appropriate minimum principle in such cases? Okay? And that's where the idea of thermodynamic potentials comes in.
Professor, what do you mean by minimum?
Minimum principle, energy minimum principle.
Oh.
What a minimum principle means, in order to have equilibrium, or when you have equilibrium, which quantity is minimized, given the particular conditions. Okay. How are the thermodynamic potentials related to the entropy fundamental relation or the energy fundamental relation? That's where Legendre transforms come in. So we learn about Legendre transforms today. Next week, we'll learn the physical meaning of these potentials and see some applications. They are sometimes, now these potentials are also sometimes useful even if their natural variables are not the ones under control. So actually, the thermodynamic potentials, you just use whichever thermodynamic potential is convenient for the particular problem you're doing, but mathematically convenient. The one that gives you the easiest calculations. Right, so we'll get more of that picture next week. But let's tackle this apparent contradiction. How can the maximum work theorem be put into practice in principle, even in principle? So, last week we had this isolated system. We had a primary system, which was the hot body. And this is the idea is that we want to convert some heat into work. We want to extract work from this hot body. We want to lift an elevator using the heat from here. Okay? And this is a controlled system. So we know its initial state and we know its final state. And in going from between those two states, it delivers a certain amount of work to this idealized reversible work source. So, you know, we want there's no friction. We want a conservative system, like a Hamiltonian system. And here, there's energy delivered in the form of heat to a low temperature reversible heat source. So this is a hot body, this is a cold body.
And the reversible heat source is the condition that tells us the temperature is going to be. Well, it's reversible.
In order for a process to be reversible, in order for the process to be reversible, the total change in entropy must be 0. So heat must be transferred between the primary system and here when there is no temperature change. Yeah. There's still a contradiction. There's something missing in the picture. Right? But there's nothing missing in the theory that we've done. What we've done, the theory that we've done, has ignored, we do not need heat engines to derive the big result. But if you want to put the maximum work theorem into practice, like make the Industrial Revolution go better, then you need to put this into practice and you have to think about heat engines. And so we derive this efficiency, the Carnot efficiency, and you see that if the temperature of the cold body is equal to the temperature of the hot body, then this ratio here is 1, and so the efficiency is 0. So it means that you don't deliver any work. It's useless. So, but if the temperature gradient is big, temperature gradient meaning the difference TH minus TC. If you put TH there, TH minus TC over TH, if you have a large TH minus TC, then you have a relatively large efficiency. Okay. So, and we also saw, as I've been saying, that that maximum work is delivered when the total change in entropy is 0. How can the primary system deliver work maximally with its temperature decreasing after doing work? So the primary system is meant to deliver work to there, and so its energy decreases. And it's not drawing energy from anywhere. This is an isolated system. While all heat transfers occur with two bodies at the same temperature for reversible heat transfer.
But you just said that they're not the same, like T cold and T hot.
Right.
Because you said because the efficiency would be 0, right? And we actually want to transfer.
Right. So we need a big temperature gradient, and yet we want all heat transfers to be between bodies at equal temperature.
But
so how do you do that?
No, but where did we get that point that they have to be of equal temperature? Like where?
Yes.
So
Entropy change must be 0.
okay. Oh, okay. And so the heat given.
What we've seen is that there was an example where last week where we had a hot body and just put it in contact with a cold body in an isolated system, and the entropy is guaranteed to increase. That's a challenge question. Right?
Okay.
So if you just put that body in contact with that body, put them together, heat will flow, but there will be an increase in temperature, increase in entropy, and there's no way that you can make that reversible if there's a temperature gradient. So what do you do? What's missing? This implies the existence of a third body or substance that acts as an intermediary between the hot body and the cold body. Okay? This substance is called the working fluid, right? Or working substance, WS, called WS, working substance, working fluid. Okay? So what happens is that the working substance is initially at a slightly lower temperature than the hot body. So we want this epsilon to be extremely small. Since there is only a single hot body, the reversible heat transfer occurs at a single temperature. And so it's isothermal. If the working substance is a gas, at this stage it can deliver some work through isothermal expansion. So this substance, if it's a gas, and let's say ideal gas, maybe I should specify ideal gas, it needs to absorb heat from the hot body, because eventually it's going to dump the heat into the cold body. That's the idea. But if it's an ideal gas, then while it's absorbing heat, it will expand, and this expansion is able to do work. So in this case, there's an isothermal expansion.
Professor, why is it at a single temperature if its temperature is actually smaller than pH?
The hot body is. I guess I'm saying the hot body is very large, so it's like a reservoir. Yeah. And actually, if it's yes, the hot body must be large. It's assumed large.
So its temperature doesn't change.
Right.
Given the low liquid.
Right. So if as long as the hot body is large, then so it's, let me write it properly, assumed large, so that means it's a heat reservoir. Then the heat transfer occurs at a single temperature. And if it's an ideal gas, and ideal gas, there will be isothermal expansion. Now the working substance is not yet at the same temperature as the cold body. it has absorbed heat isothermally. And so in fact it's at the temperature of the hot body. So somehow its temperature has to be lowered. So how does it do that? Well, it's got to deliver some work to drop its temperature, to drop its internal energy, basically. But while it's delivering work, you don't want to lose any heat. So you want to use as much heat as possible and deliver it as work. So you don't want to lose any heat. So in this step here, you want an adiabatic expansion. Okay. Right? So you keep expanding adiabatically until the temperature reaches just very slightly above the temperature of the cold body. You put the working substance in contact with the cold body, and it's a single reversible heat source, and let's say it's large cold heat reservoir. So heat reservoir. So it's a heat reservoir. So the working substance dumps heat into the heat reservoir, but the heat reservoir is so big that its temperature doesn't change. So this happens isothermally, and if it's a gas, it would dump heat and it will contract. So you have isothermal compression. Okay. And then the working substance is compressed further adiabatically to raise its temperature to the hot. You got to get the temperature of the working substance back up to the hot same temperature as the hot body. So you got to do a little bit of work on it. Yeah.
Can you explain again the process between the working substance and the cold reservoir?
Mm-hmm.
The single
large heat reservoir, which is reversible heat source.
Yes.
Okay. So just assuming it's a gas, it's a PV diagram. It's sort of a gas of some sort of molecules. Ideal gas. So it starts off at the same temperature as a hot body. This isothermal heat absorption, and then it's got to drop its temperature to the temperature of the cold body, which will be down here. This is adiabatic because you don't want to waste any heat. Then you go up, isothermal. So it dumps its in this step here. It dumps the working substance dumps heat into the cold reservoir.
So the reversible heat source absorbs the temperature.
The heat from the
heat,
working substance.
So it's a gas, so it will not expand.
Oh, well, you don't know what the reversible heat source is. It could be the environment, like the air. In fact, that's what it is usually. Or a river.
I don't understand the term compression because.
This one, its volume decreases.
Because the pressure.
Oh no! If you have a balloon and you put the balloon you blow up the balloon and you put it in the freezer, it will get smaller because it's dumping heat into the freezer.
But then, Professor, the last process, what happens in that?
This one?
Yeah.
You have to do some work to compress it and raise its temperature.
So we would have to do as
some external. Usually it's like a cylinder, and you spray some diesel in here, and you put a spark in there, and it explodes. Just that.
So what's the reversible?
And it compresses the gas.
The reversible working substance?
Diesel actually, that doesn't have a spark. Sorry, diesel. I think what happens with the diesel engine? I think it's been ages. can't remember about engines, but I think the gas gets compressed and its temperature increases, and it's so hot that the spray just explodes. Yeah, that's a diesel. Whereas petrol engine has got spark plugs. Yeah, I think it's something like that. I'm not very technically minded about motors.
Like, what in a normal case, as you said, the reversible work system is the atmosphere or something. So
No, reversible heat source.
So what's the reversible work assumption? Is it the same as the working fluid?
It's like an idealized powertrain in your car. So the cylinders go up and down, and they drive the camshaft, and the camshaft drives the axle or something. The axle drives the wheels. And if all that was frictionless, totally frictionless, and it'll be like a reversible work source. Except part of the reversible work source is the reversible work source is basically all the possible components that can do work sort of lumped together in one conceptual unit. So this bit here, where the cylinder is compressed, would be a reversible work source, even though it's not the wheel.
And Professor, the adiabatic work that the work consumption does, what does it do
On some machine, a cylinder or something. This one?
Yeah.
Yeah. Well, that would be, let's see, it's expanding, so
it's like piston expanding.
yeah, this is an expanding piston.
So it's delivering work. So it's the reversible work. So in this case.
So it's delivering that to the reversible work source.
Yeah, and as long as there's a positive, as long as there's an area, a non-zero area enclosed, this is the work done. It's the area between the cycle. So yeah.
We have to do the compression. As in we have to compress the
yes, this one.
This one.
But yeah, we have to something external has to compress the cylinder, for example. Yeah. So this is where actually maybe it's a combination of the momentum of the car or something, and then yeah, I'm not sure. You know, I'm not exactly sure. There's many different ways of making it work. This is the principle, and there are thousands of ways, or hundreds of ways of making it work. That's what these automotive engineering guys do. Okay, and of course, what I've just described is a CARNOT cycle. If this was not a heat reservoir, if this was not big, if the hot body was not very big, or the cold body was not very big, then its temperature would change, and you would have not an isothermal process, but maybe some kind of curve in the PV plane, other curve, not an isothermal.
And Professor, how do you know that S is 0 plus S is 0?
Because every heat transfer occurs at zero temperature difference there and there. So there's no entropy change in the isothermal process. And there's no entropy change in the adiabatic process because it's adiabatic.
So we use the working fluid to be able to have a reversible process.
Yeah.
Because without the working fluid, the cold and the hot body would have to be in contact, which makes it reversible.
Well, without the working fluid, nothing would work. Nothing would happen. Yeah. So since all processes are quasi-static, the cycle takes a very long time. So the power, in fact, tends to zero. So the power, you can't actually get any power out of the CARNOT cycle. It's useless practically, but it gives you an upper bound on the efficiency. There are other more practical measures of efficiency, which you can have a look at the end of that chapter, chapter 4 in Callen. It's really good. So it's endo-reversible or something cycle. So efficiency of nuclear power stations, coal stations, coal power stations, some other types. And it shows that nuclear power stations are actually really right up against the limit of efficiency. And so a more realistic power, I mean, there are more realistic measures of efficiency, which which are important if you're into applied physics. And it's very interesting stuff, good problems.
No, Professor, how do you know that the limit of the process is there, as in the quasi-static limit is defined? Because we said that the working fluid is at the temperature that's epsilon minus TH. And then we said that it's at the temperature TC plus epsilon, which is a bit higher than to approximate that the temperatures are together, so there's no heat transfer when temperatures are different. How do you know this epsilon doesn't really make a difference?
It's designed that way.
As in, is there such an epsilon?
You make epsilon as small as you want to make it as close as you want to the ideal. So it's an idealized limit. It doesn't exist, but I mean, in practical reality, it's just an idealized quantity. All right, so here's an isolated system. Here is the hot body. It dumps heat QH into the working substance, and these are when the that and that are at the same temperature. And the working substance schematically dumps heat QC into the cold body, and this is a reservoir. So these are both reservoirs, so they're big, so they don't change the temperatures as they give up or accept heat. And so the total change in entropy is a total change in entropy of the hot body, total change in entropy of the working substance, total change in entropy of the cold body. Now, the hot body gives up heat, so that means its entropy change is negative. It's minus absolute value of QH, just to make sure that the numerator is negative over the hot temperature, plus, now, the working substance, and the cold body accepts heat, so that's plus mod QC over TC. And now the working substance goes around in a cycle. It ends at the same state where it started. So its change in entropy is 0. Yeah. Because entropy is a function of state, and if you start and end at the same state, you've gone around in a loop. Means that there can't be any difference. The difference is 0. And since everything happens reversibly for maximum work, because we're under conditions where maximum work is delivered, the total change in entropy is 0. And that gives us an equation, mod QC over mod QH equals TC over TH. And finally, conservation of energy. The work delivered to the reversible work source is a change in internal energy of the hot body plus the change in internal energy of the cold body. But so that's this minus the heat that is that there's a work delivered to the reversible work source minus the heat that's taken out of the hot body, plus the heat that's taken into the cold body. That has to equal 0, because energy is neither created nor destroyed. So that tells us that the work is the difference between the heat given up by the hot body and the heat taken in, or the magnitude of the heat, So just manipulating that, you can just check it out for yourself. You get this equation, that the work delivered to the maximum work delivered to the reversible work source divided by the heat that's given up is equal to 1 minus the temperature of the cold body divided by the temperature of the hot body. Now, that's the work that you get out. That's the heat that you put in. So it's what you want over what you have to pay for, what you have to pay to get it. What you want over what you pay to get it, That's efficiency. Because it's a good definition of efficiency because if you don't get much work and you put in a lot of heat, this number's small. Okay? On the other hand, if it's big, then you get a lot of work for less heat. Okay? So that's that, and so that's again the Carnot efficiency from a completely different angle. Right. The connection with general heat engines is that the Carnot cycle is fundamental to the traditional development of thermodynamics. Any quasi-static cycle can be decomposed into an infinite superposition of Carnot cycles whose thickness, which is the length of the isothermal legs, tends to 0. So basically what you do is, here's an arbitrary cycle, say in the PV plane, it's got to be in the PV plane. And so there are isothermals and isothermal and adiabatic, isothermal, adiabatics, like that. In fact, that'll be sort of a little bit like that. And this is a large Carnot cycle. This is the actual thing that you're trying to approximate. If you make these smaller and smaller and smaller, thinner, like that, you can cover this cycle in very narrow Carnot cycles, and all the maths just works out. I'm not going to do it now because it's not directly relevant to what we need to do. But if you're interested, it's very nice. It's a very nice result. It works out. You can just read these two pages from 2 or 3 pages from Zemansky and Dittman that explains how to construct that analysis. Okay. Oh, okay. Here's the picture that I was trying to draw, and it turns out that it's a very nice result. You get that when you do that, you get that the sum over the Jth heat transferred over the temperature, the Jth temperature equals 0, and then as you take the limit as the number of these cycles tends to infinity, the sum turns to an integral, and you get that. And then this thing here, so it turns out that this is the traditional development of thermodynamics. I think this was by Clausius around 1850s. And so you get that, and this was defined as the entropy. I think he came up with that word. Yeah. So, I mean, this is very interesting, but it's a little bit beside the point from what we need to do. Okay. Right. So what I want to do is get into the energy principle, energy minimum principle. So, up until now, we've seen that for an isolated system in equilibrium, the entropy is maximized at a constant energy. Why is the energy constant? Because it's an isolated system. Okay. So the entropy is maximized subject to the condition that the energy is constant. So if this is the entropy surface, okay, and so there's the entropy. We're plotting. This is a graph of the entropy function. Here, entropy is a function of the energy, and here is just one other extensive parameter. Okay. So if the energy is constant, and you pick a number, the total energy of the isolated system is there, and there's a plane that passes through that point, okay, or hyperplane in general, okay, and that intersects the entropy function, and it is some curve here. This is very idealized, but the surface can be quite complicated, but it doesn't matter. It's the idea. And then subject to this condition that the energy has to be this, the system, when it's in equilibrium, finds the point where the entropy is maximized, subject to this condition. Okay. Now, what we want to prove is that, alternatively, the equilibrium condition is this, that at constant entropy, in other words, at the maximum entropy, because entropy has to be maximized, if you take that maximum entropy value, and under that condition, you minimize the energy, then now there's a value of entropy which passes through that same point. That's the maximum entropy point there. And now there's a plane that passes through that point there, that entropy value, and it intersects the entropy surface like this. And then there are many, in general, many accessible energy values in a sense of conservation of energy, but the system minimizes the energy. So to minimize the energy, this is towards negative energy that way, and towards smaller energy that way. Smaller energy. And here the energy is minimized. What we want to do is go from this way from that to that.
Perfect.
Yeah.
But last time you said that all the points on this on this surface are equilibrium points.
Yeah, they are.
But then why does it choose the point that's the top for the energy if all of them are equilibrium points?
You mean this one? Or this one? Which one? This one?
Top one?
Yeah.
We said that the entire surface is equilibrium point.
Right.
For any U and VU, you just have one S value.
Yeah.
But then you said that we maximize the S for one
Given the conditions. So you have an isolated system.
Yeah.
You got a particular value of U. You get another isolated system. You might have a value here, and then the entropy, maximum entropy up here, will be that one. So these are equilibrium points, but under different combinations of U and the extensive parameters. So given the conditions, the system, when it reaches equilibrium, finds one of these points.
So each of these points is a maximum for a certain U?
Yes. Yes.
But then we can see that there's only one per plane. Per one value of constant U, there's only one S. So there is no dependence on the extensive parameters.
The extensive parameters that are chosen. This is just one. There could be many extensive parameters.
So suppose
and so the one that is chosen are such that that point is highest.
But don't we control the extensive parameter and U?
So we control it and fix that state. Let's say we fix that. No, this is a composite system. So this is back to, for example, you have two subsystems with many possible combinations of x1 and x2, and any one of them satisfy the energy condition. So go back to.
So this is not.
Go back to. So depending on the temperature, go back to the first assignment, and I think the third question of the first assignment, where you have the two subsystems. That's what's happening here.
So these are not equilibrium points. There.
These are right.
They are. Every point on here is an equilibrium point, but
they're energy conservation points.
And an equilibrium.
in order to be plotted on here, you got an equilibrium point.
But then if it's
But there's only under this condition, under these conditions, there's only one that maximizes entropy.
but the condition for equilibrium is that you maximize energy.
Yeah.
So there's only one line, one curve.
Yeah. No.
No, this like that goes like that.
Which one?
The outside.
No, but given one constraint, right?
It's relative to the okay. Think about it later. It's relative to the constraints. So if I have two subsystems divided by a wall that's impermeable and adiabatic and everything, I can be there. I take the wall away, the system ends up there. That's what's happening.
Okay. So everything is subject to the constraints.
Right, to the constraints.
So
Right.
it's the maximum entropy given the constraints.
Correct.
Not for like free.
Of course. Otherwise, I'd be keep going up there somewhere. Okay. So theorem: in an isolated system in equilibrium, the entropy is maximized at constant energy U if and only if the energy is minimized at constant entropy S. Let's see why this is so. So this proof is a physical argument, right? So I think it's always very useful to understand or be able to prove things using a physical argument before you get into a mathematical argument and you get lost in symbols. So let's have a look at the physical argument, but we'll only go in one direction. So prove that given that the entropy is maximum, then the energy must be minimum. So in an isolated system, suppose the entropy is held fixed, and in equilibrium, the entropy is maximum. Suppose that the energy was not a minimum. So let the system do work at constant entropy. Convert all the work into heat and pump the heat back into the system. So the energy remains constant because, well, the final energy is the same as the initial energy because you've got an amount of work and you've converted it all into heat and you've pumped it back into the system. So there's no change in energy, but the heat input, and do it quasi-statically, so this is happening, so this is true. The heat input causes an increase in entropy, but that contradicts the assumption that the entropy was maximum. So, if the entropy was not maximum, so suppose the entropy is maximum, if the energy is not minimum, then we could lower the energy by letting the system do some work. And then you convert that work into heat using any contraption and pump it back into the system. And then the entropy of that system must increase. But then that means that the entropy wasn't a maximum.
But it's not necessary to convert all the work into heat, right?
No, but yes it is, because you want the total energy after to be equal to the total energy before.
But that's not possible, right? To convert all
Work into heat it is.
like current.
Yeah. Work into heat it is. Yeah. Heat into work? No.
The opposite.
Yeah. Yeah. So the physical argument has proven that maximum entropy implies minimum energy under conditions of constant U here, under conditions of constant S there. You need to go the other way. It's problem 5.1.1. It's just optional. You don't have to do it, okay? But you can try if you want. Now, mathematical proof. So we proceed in the same direction as in the physical proof. So S maximum at constant u implies u min at constant s. And leave the reverse direction as an optional exercise. So, let's just orient, before we dive into the symbols, let's get some orientation. Let's think about it. Right? So we assume that the entropy is maximum constant u. So it means it's concave down. And in high school, I always thought of it as concave down if you have a maximum. Just means that the second derivative in any direction is negative. Second derivative is negative. In any direction. I mean, in all directions. But the energy is constant, so we only need the direction, the second derivative in the x direction, where x is an extensive parameter. In fact, it's in all the xi directions, all the directions of all the extensive parameters. Okay. But we just choose one of them. So we want to use that fact, the fact that the second derivative in the direction of x, of the entropy function, is negative, to show that the second derivative of the energy in the direction of that same extensive parameter is positive. So then it's like that, concave up. So we want to use that second derivative and end up with this second derivative. Or the other way around, we want this second derivative and derive that second derivative. That second derivative is going to be negative, and we must get like negative, to give a positive. That's what we're aiming for. This is what our maths, that's the direction that we're going to go in our proof. Okay, so we know what we're doing. So we must convert a second derivative of u with respect to x at constant s into a second derivative of s with respect to x at constant u. Okay? So we've got to do some gymnastics using the identities we proved in the first lecture. Okay? So let's do it. So let x denote a particular extensive parameter of some system. Let P be its associated intensive parameter. So P is not pressure. P is any intensive parameter that's associated with this x. Okay? So it could be T minus P mu or whatever. No, not T. So, in other words, what we're saying is P is du by dx at constant s. Obviously can't be T, because we're keeping s constant at maximum. Okay. And all the other extensive parameters are fixed. So I could have written x1 up until xn or whatever it is are fixed, but except not equal to xj or xj, whichever one is here. Okay. But I'm not going to worry about writing all that because it'll clutter everything up. All right, so what we want is to we've got derivatives with respect to u. What we want is to get derivatives with respect to the entropy. So there's an identity that tells us how to. This is at constant s. So that's ds. So we've got to put a minus sign. ds by dx, ds by du. And that's x, so that's going to be a constant u. That's u, so it's going to be a constant x. Okay. So that's using that. And now we started with derivative with respect to u, and we've got derivatives with respect to s. Good. So on the right track. Next, you recognise that that's 1 over the temperature. No, it's not. Yes, it is. That's 1 over the temperature. So that's minus ds by dx divided by 1 over t. So that's minus t ds by dx at constant u. Okay. And what do you think the next step is?
Ds by dx. This is 0, 0.
dS by dx must be 0 because entropy is maximum. It's this is just the first derivative of the entropy in some direction, in the direction of u, but it's a maximum, so this has got to be 0. So that's 0. So that's saying that the first derivative of the energy in any direction besides the entropy is 0. So it's, and what does that tell you?
It's an extreme.
Sorry?
It's an
Extremum. Therefore, u is at an extremum. So it could be maximum, minimum, or point of inflection. Okay. Right. So what we've got to now investigate is a second derivative of u. So what we need is d2u by dx squared at constant s. We need to investigate that. And that's dp by dx at constant s. Okay. Now, again, we want derivatives with respect to s eventually. So now consider p to be a function of u and x. The reason why is that then eventually we're going to have derivatives with respect to of s with respect to u. We're making we're putting in u as one of the variables instead of s, because we want eventually we want derivatives of s with respect to u. So we've got to make sure that we express things in terms of u. That's why we do this step. So now dp is just dp by du at constant x dx plus dp by dx at constant u dx. And this is all happening at constant s. All of that. There's a condition that's there, always there in the background, right? That we're working under. So now I'll go, but what about the total derivative of dp by dx? Well, that's dp by du at constant x. dx by dx, so it's just 1 plus dp by dx at constant u, dx by dx. But dp, okay, that.
Isn't there a u?
So u.
The u.
This is supposed to be du.
Yeah, it's supposed to be u.
du by dx, yes, thanks. Messed up. That's du, yes. Okay. But dp by du at constant x. And this is now du by dx at constant what?
S.
S. Yeah. And we just saw that that's 0, so that term falls out. We got that, but that's dp by dx at constant.
U and s.
U
And s, of course.
and s, yeah. Okay. But that there, now this is happening at constant s, so I could have said that that's dp by dx at constant s, which is what we're looking for, which is equal to d2u by dx squared at constant s, and this is a quantity that we want to show is positive. So that's that. And now we want to manipulate this somehow to get derivatives of the entropy.
So how did we get the left one?
This one?
The second derivative?
This one? This one?
Yeah.
Because P is the first derivative of U with respect to X.
Oh, okay.
That's the intensive parameter
Okay.
in the energy representation corresponding to the X extensive parameter.
Okay.
Just dP by dx. And what we want is to introduce the entropy but we saw here that P is that ratio there. Yeah, that's that bit there. So what we've got here, we've got d by dx of P constant U. So here we've really got minus ds by dx at constant U over ds by du at constant x. Okay? Is that okay? Yeah. So, because that's P. And that's what we had. We already did that bit there. It's P. So now we've got derivatives with respect to S, which is what we want. And also we've got first derivatives with respect to S there, and another derivative of all that. So we're going to get second derivatives with respect to S, which is really good.
We have a constant x and a derivative with respect to x.
Yes.
Yeah, because this thing here is a function of U and X.
But
Even if it's
That's
if it's
the
derivative at constant X, it's still a function of U and X.
Yeah.
Okay. And then both this is a function of U. That's a function of U and X, and that's a function of U and X. Okay. And this is d by dx of that. So I need to use product rule. Okay. And so what you get, use product rule. Okay. So that's, just write one more line out, minus ds by dx at constant U, ds by du to the minus 1 at constant x. And all this is happening at constant U. And so that's, now use product rule, so do the first, so that's d2s by dx squared at constant u ds by du power minus 1 at x, and there's a minus 1 missing there. Minus 1 missing there. Plus ds by dx times minus, it's actually minus. I think it's supposed to be a minus there, because it's minus.
Oh, minus 1.
Yeah, minus 1 times minus 1 times minus 1, so it's going to be minus there. So that's supposed to be a minus. Minus there. And that's going to give, now the derivative of what's in the bracket, so that's d2s by dx du times ds by du to the minus 2. But all that stuff doesn't matter because ds by dx, what's that? Yeah?
In the lecture note, you don't have a minus in front of the d by dx.
Yes, I know.
Professor, you just took that minus in the previous paper out, so you wrote another extra minus, I think.
Here?
No, can you go back to the...
So look.
See, if you look at the step on the paper on top, you just took that minus outside.
Oh,
Yeah.
yeah, thanks. So that's going to be minus minus, so this is going to be plus, yeah. So this is plus. Right, thanks. But what happens with this term here? It's 0, why is that?
Yes, by dx.
Because entropy is maximum. We're working under the condition that entropy is maximum. So that's 0, forget that. And then what's ds by du?
1 over t.
1 over t. 1 over t is t. So that's, there's a minus sign there. Because there's a minus sign there. So this is minus t d2s by dx squared. And what can we tell about that? Can we make any concrete statements about that?
This is concrete though.
Yeah.
This is concrete though.
S is a maximum,
Yeah.
so that this second derivative must be negative. Temperature is positive, that's negative, so this must be a positive quantity.
So that's u is concave.
And so so what we've just shown is d2u by dx squared at constant s is a positive quantity. It's concave up. And x is arbitrary. X is an arbitrary extensive parameter, excluding s. So therefore u is a minimum. So that's the mathematical proof in one direction. And you can see how we try to make sense of the direction of where we're going mathematically. We want to end up with derivatives of, we started with the derivative of energy with respect to an extensive parameter. We want to introduce derivative of entropy with respect to an extensive parameter. That's what. All right. So that's that. Let's just have a look at the typical physical interpretation. Suppose we have an isolated system and it has a fixed entropy because it's in equilibrium. So it's at a maximum entropy given the conditions that it's under. So it's got particular values of V1, P1, T1, V2, P2, T2. Initially they're separated by an insulated wall, impermeable and rigid. And in that case, they would be, and initially this is an adiabatic wall, and that's in equilibrium, and the total entropy is the maximum possible given these values. In that case, the entropy would be at this point here. That would be that point there, roughly, for example. Okay? And then you replace the adiabatic wall with a thermal wall that can transmit heat. The system readjusts itself. The entropy climbs up at the same total energy, and the final equilibrium point is this one here. Okay? So initially, the entropy was down here somewhere, and the system rearranges itself spontaneously without any outside help. Any spontaneous process, the entropy must increase. So it must go up here like that. And it ends up at the maximum possible. When it gets up here, it can't rearrange itself anymore. That's an equilibrium state. Right?
So, Professor, the way we can think about the isolated systems is that there is an equilibrium that's not an even. It's something that's frozen. It's not even. It's not properly an equilibrium.
It's properly in equilibrium because there are two separate isolated systems.
But S
Is the rule is
yeah, the S is also S, but then it doesn't lie on a maximum.
Because we're given that the extensive parameters, we're given certain constraints, and it forces the system to be there. And it's in equilibrium. That's where it has to be given those constraints. take those constraints away, and it rearranges itself spontaneously, the entropy's got to increase at that same constant energy, ends up there.
But it's not really at the maximum entropy.
It is. That's the maximum entropy, given that this constraint is there and the other dimensions are sort of given. So now you allow heat to flow. What is the final equilibrium state? That's the question. So now we have an extra equation. I mean, before we were using the maximum entropy principle to get our extra equation. Now we're using the energy minimum principle to give our extra equation. So conservation of energy gives us that the total energy is energy of the first subsystem plus the energy of the second subsystem. That's got to equal constant, which means that the differentials, the differential of the total energy equals du1 plus du2, and all the other conditions, dvi are 0, dni are 0, all the others. And now du, now there's no volume change, there's no work being done, so the entire internal energy change is due to heat, quasi-static heat transfer, so it's T1 ds1 plus T2 ds2. And that's got to equal 0, and that gives us a relationship. Now S is a maximum in the final equilibrium state, so S1 plus S2 equals S, so ds2 equals minus ds1 from there. So that tells us that ds2 is minus ds1, so we factorize the ds1, we get T1 minus T2 ds1 equals 0. That's arbitrary, that's for arbitrary ds1. Which means that T1 minus T2 must equal 0. This coefficient must equal 0. So T1 equals T2 must be the equilibrium condition. So we derive the same equilibrium condition as we derived using the entropy maximum principle. Obviously, all the other for all the other situations like particle transfer, volume transfer, you get the same condition. They're equivalent. Okay, so let's have a 10-minute break and we'll get into the Legendre transforms.
So Professor?
We'll just have a question, yeah?
When we have one system and we only have, I suppose it's just a function of d and u.
Yeah.
And because it's a function of u, we have a surface, right? So the case, the equilibrium case, depends on V. If I set my V, then I'll have a force Q.
Well, yes, but now you're talking, what you just described is an oscillated system which is simple in the sense that it has no subsystems.
Yeah.
Yeah, so that there's a U and V combination that's forced. Yeah, so then, and then the system chooses the maximum entropy given that V and that U.
Which is only 1 point.
Right.
But if we have another degree of freedom, then the system has to choose, essentially.
Yeah. And so that essentially what that's saying is that the entropy maximum principle gives us another equation that has to be solved, and it fixes a single point out of many possible points.
And the degree of freedom comes from the very little volume, for example. If I'm mixing two systems, I just need the sum of the volumes to be constrained.
Right.
Yeah. Sure, definitely.
Okay, so let's finish it off. So the main part of today is, the most important part is the Legendre transform representations. So what if the variables under experimental control are not UVN or SVN, but some other set like TVN, TPN, TPmu, or some permutation? And in the entropy representation, the fundamental relation is S as a function of U, V, and N, V. Now this contains all the thermodynamic information about the isolated system. What about the function S as a function with the variables T, V, N? Does that contain all the information? Why or why not?
T is a function of U, V, and N in general. So I guess it would still contain information.
Anyone else?
There might be a redundancy.
What's T? What's the definition?
D over ds. That constant T.
So in the entropy representation, what is it?
It's 1 over du by ds by du.
So 1 over T is ds by du, right?
Yeah.
At constant Vn. So if I write this, I'm actually replacing u with the derivative of S with respect to u. Right? So actually, what's happening is that I'm losing information. I'm losing a lot of information. Just to give you an example, let's have a look at f of x, y is x plus y. Okay? And what if I replace x with df by dx? Now df by dx is 1. So everywhere where you see x, you put in 1. So now the function of f as a function of df by dx and y is now just 1 plus y.
But wouldn't the function and form change?
No. I'm replacing this variable by the derivative of the function with respect to that variable. Right? Way different. And you've lost a heap of information.
But it just simply isn't the case, is it? As in, this is not what f is.
It is, yeah. So if I just replace S with T, obviously if I have the energy equation of state, the thermal equation of state, for example, for an ideal gas, U is C and RT, okay? Then I can invert T and I can put U in, and then that's equivalent, that's the same thing. So this plus the U as a function of T, this equation of state, has those two equations together contain the same information. But if I don't have that equation and you just give me S of T Vn, you're not giving me all the information.
Because when you're integrating back to find S, there's a constant of integration.
There's a constant of integration, right? Okay.
So what are we integrating? Oh, T. What are we integrating by S?
So, but in experiments, you do need to consider other combinations of variables to be controlled. So it's useful to formulate thermodynamics with other sets of independent variables and properly so that you can write down a fundamental relation and not lose information. And the natural variables are the variables that are controlled in the laboratory. So you want to replace the variables U, V, and N with something else, or S, V, and N with something else. In fact, we're talking about slopes of S with respect to U, or slope of S with respect to V. I mean, derivative, right? Slope, right? So you're replacing the variables by slopes. Right? That's essentially what you're doing, because all these intensive variables are just derivatives for the fundamental relation, the entropy representation of energy. So when I get to the idea of Legendre transform, so what we want is to represent a function in a different way, such that that process is natural and works well. We're going to represent the function in a completely different way, completely different concept. So let's suppose we have y as a function of x. The graph of the function, let's suppose that the graph of the function looks like that. And what does it mean when we say a graph? So to any point x, we associate y of x. And so that point there is the point x, y of x. That point there in the plane. And point-wise, I do that for every x in here, and I do that. So I get a curve like this. That's how we build up the graph of the function. But there's another way we can specify this curve. What if at any point there, say, I take the tangent at that point. So the tangent, and I need one more number to specify that uniquely. And I specify the intercept with the y-axis. So that number, if you give me that point and a slope, then I know that I need to start from here and head out in this direction, and I just have that line there. That line there. Now, you give me that point and another slope, and I'll just head out in that direction, and I'll have that line there, that point and another slope, that line there, and if you give me, for every point along here, a slope, then I can make an envelope, put all of these straight lines together, and the envelope of all of these will be that curve.
What do you mean by envelope?
Envelope is
in this case.
envelope.
You just put all the lines and that what's above.
It's what you see here.
Okay.
Yeah. So that there is another way of describing that curve. Okay. But what we've done is now we've got a point and a slope. And since what we want to do is replace variables with slopes, then maybe this is the right way. This might have something to do with it. So, so there's y and x, and there's some messed it up. Like that. So there's an xy point. Specify an xy point. I mean, suppose we're interested in that point. Now that point has a tangent to the curve. And let's say that this is the point, this point here is the point 0, and let's say it has some value psi. And then this is the rise, this is the run. The rise over the run is, well, what's the rise? It's the value, the y value there, which is y, and the y value there, which is psi. So it's y minus psi over the run. The run is the x value there minus the x value there. So it's x minus 0. And we just define that to be about the quantity p. So the first equation is, we'll just isolate the psi. We want psi equals, put x over there, so we have px. as px minus y, but that's minus psi, so that's going to be psi is y minus px. And that there, now that p is that slope is the slope of the tangent. And so this is called the Legendre transform of y of that, because we're replacing, because what we're not going to use the word replacing, we're subtracting the slope with respect to x times the value x at that point. Okay, so what this does now is, now that's a given number, so it converts a description of a function from y is a function of x to the description psi is a function of p, where p are these slopes.
But then we still have the x.
So if x and y are given, if x and y is a given point, or a set of given points. So x and y are known, but p is not. Or size of p. The p be the variable, so p is the control variable. The point is that we have a function of a slope.
So we define the function in a different way. It's like a different coordinate system.
Yeah, completely different way of defining the same function. Using this type of geometrical construction.
And the relation helps us change from one description to the other.
Yeah. So now you're given y is a function of x. So this is the second equation. So the first equation is this one for the psi. The second equation is that you're given y as a function of x. So you're given that equation there. Differentiate to get the derivative dy by dx, which we call p. And that is a function of x. So in other words, that's p of x, okay? So this is the third equation. So, what you do is now, you eliminate x and y from there to get psi of p. So
So where's this side?
you see, we're given y of x, and you take the derivative and you get p of x equals that function of x. So what if you invert this? You get x as a function of p. You put x as some function of p in there. You get p times p squared or something. And then y is a function of x, but x is a function of p. So you have y as a function of x as a function of p. So this is something like p cubed minus p or something. So you've only got p's left in here, p's left in there, and p's left in there. So you get psi as a function of p. Okay. And you can go in the inverse direction, reverse direction, from psi of p you want y of x. You can just read that for yourself. In general, given a hypersurface, so y is a function of t plus 1 coordinates, and we're assuming they're Cartesian coordinates. This is a Cartesian coordinate system. Okay, so that's important. Yeah. Yeah. The derivative, the kth derivative pk is dy by dxk. So this is going to be these are going to be extensive parameters. These are going to be intensive parameters eventually. Is the slope of y in the direction of xk, of the xk axis. To replace the first m variables, you apply the Legendre transform. So there's the function y that you started off with, and you want to replace the first m of these x's with m slopes with respect to these derivatives with respect to these variables. Derivative with respect to y with respect to x naught, y with respect to x1, y with respect to xm, or m minus 1. Okay. So then, you subtract from y the sum of from k equals 0 to m minus 1 of the kth slope times the kth variable. And so then you get psi as a function of the slopes, and plus the remaining variables. Okay? Right. So an example that you know, minus the Hamiltonian, I've got the wrong way around, so minus the Hamiltonian is the Lagrangian minus the sum from k equals 1 to the number of phase space coordinates, or the number of the dimension, number of q's and q's, which is the number of p's, times the derivative of the Lagrangian with respect to qi dot, qk dot, times qk dot. See, so you are replacing, in the Lagrangian, you're replacing the kth velocity by the kth canonical momentum, pk. So the transformation from the Lagrangian to the Hamiltonian, which we learned a few weeks ago in the classical mechanics part of quantum, QM2, is the Legendre transform. And it was important, somebody asked a very good question, it was important that is a Legendre transform, it was important that that is a derivative of that function with respect to that variable. That's what makes it work. What makes it work is that this is a Legendre transform, and it works because of what I just showed you. Yeah.
Is this unique? Like this kind of are there other representations for the same function? That conserve the information.
Well, is it unique? So what you're really asking is,
I mean,
can you have another, can a point and slope
not necessarily
describe a different function, or can be there another slope and point?
or not only Yeah, but I mean some other, like for this we use the description in which we had an intercept and a slope. But could we use slope and something else? I don't know.
That can be the sparse representation when you come up with it. Okay. And Callen, I forgot the name of the French guy who came up with this, but it's in Callen. But it just turns out to be extremely useful. Okay, so let's have a look at examples applied to thermodynamics. And so this is where thermodynamic potentials come from. So we want to find, the Legendre transforms of U of S V N. The Legendre transform of U S V N give the thermodynamic potentials so the first one is the Helmholtz free energy. Has anybody heard of the Helmholtz free energy before? Where did you hear about it? Gibbs free energy, Helmholtz free energy. Where have you seen those before?
Chemistry.
In chemistry?
Yeah.
Okay, so this is where they come from. So F, T, V, N. So the natural variables are T, V, N. So what's happened is we've replaced U with the slope of U with respect to S. Okay. So the natural variables are T, V, N. And so you're given, this is the recipe, given U of S, V, N, you find T equals du by ds, obviously at constant Vn. Anything else? Now that means the temperature is a function of S, V, and N. And then you write the Legendre transform. So you start off with the function u, you subtract from it the slope with respect to the derivative of u with respect to s times s. That's f. Okay. And then you eliminate u and s in favor of T, V, N. So here, this gives us T as a function of S. So if I invert that to get S as a function of T and Vn, if I substitute that into there, I would get U as a function of T and other things. And then that means I have here like T squared times V times N something. S has disappeared. Now substitute that in there, I get an expression involving T, V, N only. And S here has been inverted, so I get TV, S is a function of TVN there. This thing here is a function of TVN. This thing here is a function of S as a function of TVN. So all that's left here is T, some combination of T's and V's and N's, T's and V's and N's, T. So you've got F as a function of T, V, N only.
But Professor, we can't do the same for two variables. As in, I can't have T and P.
Sure. Sure you can.
But then how would I write the S?
We're getting to that. This is Helmholtz free energy. Just wait. So this now there's a nice way of denoting this is a Legendre transform. The Helmholtz free energy, you can denote it as, just put three bars like this to mean denote U in square brackets T, like that. Okay. So that means this means that the Helmholtz free energy is the Legendre transform of U, where the variable T replaces the appropriate variable U. Okay, there's that. Now, dF, now f is a function of TVN, so dF is dF by dt at constant Vn dt plus dF by dV at constant Tn n dV plus dF by n at constant Tv dn. Okay. And also from here there, the differential of dF is du minus TdS minus SDT. Okay. But du is TdS minus PdV plus mu dn. Here we have minus TdS minus SDT. So TdS cancels. We have minus SDT minus PdV plus mu dn. dF. It's also important. Okay. Right. So next one is we want the Legendre transform U where we eliminate V in favor of minus P, and that's going to give us the enthalpy. The enthalpy is a function of S, P, and N. It's called enthalpy. Another favourite potential that chemists use. That means you're replacing V with minus P. So H is, now you start off with U, you subtract the slope of U with respect to V times V. So that's U plus PV. Okay? So in other words, so what you do, in other words, given U of SVN, you find the equation of state, minus P is du by dV, constant Sn, and that's a function of SVN, that derivative there. So here you can eliminate that's like a known function. If you're given what U is, you take the derivative, that's some mix of SV and N. So you invert the P function to get S as a function of P, V, N.
Should be V as a function of V.
Oh, sorry, V is a function of PSN, that's correct, yeah. And substitute into, so here U is a function of SVN, and V, so you get V is a function of SPN. So put that there, and then S, so V is a function of, and then put that V into there. So all you're left with is some combination of SPN there and SPN there. So H turns into a function of S, is a function of SPN. Okay. The H equals blah blah blah. So you can do that as an exercise. You're going to do it about 1,000 times anyway. So you can do it now. Gibbs free energy. What's the Gibbs free energy? It is the Legendre transform, U, and it's T and minus P. So, and so it's a function of, G is a function of T, P, N. So the Legendre transform that gives G is U minus TS minus minus P, so it's plus P, V. That's the Legendre transform. And so dg equals, and you can do an exercise. So then using the equation of state, using two equations of state, eliminate U, S, and V, and so you get this thing here. So G is a function of, eliminate that in favour of T minus P, and basically get that. Okay? The last one, that, I mean, there are many types of potentials, many potentials that are useful. Zemansky and Dittman have a page with a list about, I don't know, 10 of them or 12 of them, and they tell you the physical situations where they're used. Very nice table. But the one that we use, these are the ones that we use most often. And there's one that we'll use when it comes to, I mean, we would use this one if we were talking about chemical reactions or where numbers of particles change. Or where a system is in contact with two systems with two different chemical potentials are in contact, and then you get equilibrium with the particle exchange between them. So something like, for example, there's a bottle, and it's at the bottom of the sea, and initially the bottle has fresh water in it, and the water is salt. The seawater is salty, and so there's an exchange of salty water and fresh water. Two different chemical potentials which are driving the exchange of particles. Eventually, equilibrium is set up where the chemical potentials are equal. That gives you the equilibrium concentration of salt in the water. But so the grand potential is U, is a Legendre transform U T U, and the symbol that we use and Callen uses is the the capital psi. So, and each psi is minus SDT minus PdV minus N du. And the Legendre transform, it's I mean, it's just that. I mean, you can write it down for yourself, okay? Because you know enough now. But finally, so this is the grand potential. It's very important in statistical mechanics. And finally, notice what happens if we take the Legendre transform U of T, P, mu. So we substitute all the extensive variables with the intensive variables. So what happens is that equals, so what's that? U, start off with U, and we subtract T times S plus PV minus mu N. And what do you think that is? Or what do you think that's equal to?
0.
0, very good. That's 0 because the Euler equation, U, is Ts minus PV plus mu N plus Ts, oh sorry, minus Ts plus PV minus mu N. Ts cancels, PV cancels, mu N cancels, and you get 0. Okay, so if you Legendre transform all the variables, you get 0.
And what is that?
Yeah, what is that term?
No, it tells us, depends on what you're looking for.
Okay. Is
That I
there
can't write that I can't write the function in terms of T.
It's telling us, don't get too enthusiastic.
Yeah.
Then Legendre transforming everything.
So you can't find the function for you need an extensive parameter. You can't express it only in terms of intensive parameter. Otherwise you get 0.
Well, this is limited to situations where there are only 3 variables to start with. S, V, N. It's saying there'll be a differential geometric interpretation of this that will answer your question. It depends on what sort of question you're looking for, what sort of answer you're looking for. All right, so next week we'll look at physical meaning of these potentials and some applications next week and the week after. Okay? Yep.
Is there any reason why it's called the grand potential?
Yes, because there's a petit potential.
Oh, okay.
Wrong, it's big. Big potential. Yep. Okay.